Viscosity versus Drag in Fluid Solutions by Louis Kudzma,
Anuj Arkatkar,
and Noah Storbeck.
Viscosity versus resistive forces are all around us today. Their goal is to slow movement. There are a few main types of resistive forces that are common in everyday life. The main three are friction, drag, and viscosity. Friction deals with surfaces interacting with another surface. Drag deals with an object's movement through fluids while pushing the fluids out of its way. And finally, there's viscosity. This resistive force also moves through fluids, but the fluid drags along with the object as it moves. Our hypothesis is, if the shape of the object is smooth, then the fluids will flow smoothly around the object, relating more to viscosity as the main resistive force. Our predictions: acceleration versus viscosity graph will appear more linear, a higher r squared, than acceleration versus velocity squared graphs. Our goal of the experiment is to determine the resistive forces acting upon a steel ball as it moves through fluids using a graphical analysis. For this experiment, we used two 50 milliliter graduated cylinders, 50 milliliters of water, 50 milliliters of corn syrup, two metal ball bearings, and tracker software. The equations used to produce the graphs are listed below.
One of the major parts of our experiment was deciding whether drag or viscosity was acting on the ball bearings more. And an easy way to do that is with these equations, solving for acceleration, graphing acceleration versus velocity or velocity squared, and seeing which r squared value is higher. So we got the position time graphs from Tracker, and then there were a couple ways to do the simulations. Option one was to use a differential equation and integration. And we decided on option two, where we use this Python simulation, and basically we checked how the graphs matched and how close they were to predicted terminal velocity.
So we begin with our discussion on the results for the water, and we see one of the big problems, which is that there are only about 7 data points across our entire set. That's just because it went too fast for the camera to catch. But even with 7 data points, we can see a pretty good linear fit for both the drag regression and the viscosity regression, though slightly better for viscosity. On the other hand, for corn syrup, we have a lot more data points since it was moving a lot more slowly, and we can see that although it's not as linear, there still seems to be a preference for viscosity over drag in our fits. Now we move on to discuss how closely the data that we get from our graphs actually matches what happens in reality by aligning our graphs of position versus time against simulated graphs using the same initial velocity and the same parameters that we got from our values in the graphs. On the other hand, when we look at corn syrup, we see that it's actually a lot better for viscosity. Not only does the graph match it a lot better, but we also see that the simulated drag has a much higher terminal velocity than it really should have, as we observed.
So from our findings, we can conclude that in corn syrup, viscosity is significantly more representative than drag for the actual motion we found. And for water, neither drag nor viscosity is more prevalent significantly. So one of the major flaws with our model is that for our syrup trials, our gravity by itself is way too low. And we think that a reason for this could be we dropped it above where the actual corn syrup was. So it had to break through the surface tension, and we're also missing a buoyancy force in our model. And that is shown in our free body diagrams here.